Okay, imagine for a second, what if we could solve humanity's energy needs, like forever, with a power source that's totally clean and practically limitless? Well, today we're diving deep into nuclear fusion, the one technology that might actually pull it off. Right, and you need to forget everything you think you know about nuclear power, because this isn't just about building a better power plant. The goal here is, well, it's almost mythological. We are literally trying to build a star in a jar. We want to take the exact same physics that powers our sun and replicate it right here on Earth. So what is fusion exactly? The basic idea is surprisingly simple. Instead of splitting heavy, clunky atoms apart, you're doing the complete opposite. You take two really light atoms, usually special versions of hydrogen, and you use unbelievable amounts of heat and pressure to slam them together. They fuse, they become a new atom, helium, basically, and in that tiny moment, a little bit of their mass vanishes and becomes a massive amount of pure energy. Now, this is so important to get straight. This is the polar opposite of the nuclear power we already have. You hear the word nuclear, and your mind probably jumps to fission, right? The tech in today's power plants. But fusion, it's a completely different animal. Yeah, and just look at the differences here. They have huge consequences. Fission splits things. Fusion combines them. Fission needs limited uranium. Fusion's fuel comes from seawater. It's everywhere. Fission leaves behind that nasty, long-lived radioactive waste that everyone worries about. Fusion's only byproduct is helium, for balloons. And maybe most importantly, safety. With fission, there's always that tiny risk of a meltdown. With fusion, a runaway reaction is physically impossible. If anything goes wrong, the whole thing just stops. So if fusion is so perfect, why aren't we all using it? Well, smashing atoms together means you have to create temperatures hotter than the core of the actual sun. And, containing that is one of the biggest engineering challenges in human history. It's actually sparked this incredible race between two totally different ways of doing it. Okay, so the first method is all about control, about holding on tight. It's called magnetic confinement. You take your fuel, you heat it up into this super hot state of matter called a plasma, and then you use some of the world's most powerful magnets to trap it and squeeze it inside this crazy donut-shaped machine called a tokamak. It's literally like building a magnetic bottle to hold a tiny star. And then you've got the other approach, which is kind of the opposite. It's not about holding on for a long time. It's about a single, overwhelming moment of brute force. It's called inertial confinement. And instead of a magnetic bottle, you take a tiny little fuel pellet, we're talking smaller than a peppercorn, and you hit it from all sides with the most powerful lasers ever built. And the process is it's mind-bendingly fast. Okay, so a tiny pellet drops into a chamber. For a fraction of a billionth of a second, nearly 200 massive lasers fire all at once. The outside of the pellet instantly vaporizes, which creates this perfect inward rocket-like implosion that crushes the fuel inside to densities and temperatures you just can't imagine. And that triggers fusion. The whole thing is over in the time it takes light to travel across a room. For decades, fusion was a running joke in science. It was always 20 years away. But something has fundamentally changed. We've hit a real tipping point, and it's being driven by a flood of private money and some massive, massive scientific breakthroughs. The game has totally changed. And a huge piece of this new era is the money. Follow the money, right? For the longest time, fusion was just for giant government labs. But now, we're talking over $13 billion in private investment that's just poured into dozens of fusion startups. This isn't just research grants anymore. This is serious commercial capital chasing what could be a $1 trillion prize. So why is all this money flowing in right now? Well, for 60 years, the absolute holy grail of fusion was something called net energy gain. It just means getting more energy out of the fusion reaction than you had to put in to start it. It was the one scientific wall that seemed impossible to climb. And then in late 2022, scientists at a lab in California, they finally did it. And they've done it again and again since. The basic science is now proven. And the pace of this is just accelerating like crazy. What took 60 years to do once is now being repeated and refined in just a matter of months. With that core science finally cracked and all this private cash pouring in, the whole race has shifted. It's moved out of the physics lab and onto the engineering floor. The new goal is to build the first commercial pilot plants. Which brings us to the final, multi-trillion-dollar question. All this progress is amazing, but when are you and I actually going to be able to flip a light switch and have it be powered by fusion? How close are we, really? So let's just go there. Let's ask that classic skeptical question. After all this hype and all this excitement, have we finally broken the curse? Is fusion still just always 20 years away? You know what? For the first time ever, the answer might actually be no. So, could we really see fusion power in the 2030s? The argument for yes is actually pretty strong. The core science is proven, the money is flowing, and new technologies like AI are making everything happen way faster. But the hurdles are still huge. Proving something works in a lab is one thing. Building a massive power plant that has to run 24/7 for decades is a whole other beast. That's a monumental engineering challenge. We have to figure out the right materials, and we have to prove the whole thing can be built and run at a price that makes sense. The scientific problem is solved, but the engineering problem has really just begun. Look, the key takeaway here is this. For the first time in our lifetimes, fusion power is no longer a question of if, it's a question of when. Yeah, the engineering challenges are immense, but the momentum is just undeniable. Moving from a civilization that basically just burns stuff for energy to one that forges miniature suns on demand, that's going to be the single biggest leap in human history. The only real question left is, are we going to be the generation that finally makes it happen?